Good morning. In today's lecture, we're going to wrap up the last several lectures. Actually, the lecture that started with the normal distribution and then moved on to understanding multiple random variables and understanding the expected value and variance of x bar. We're going to put all of that together into something that's called the Central Limit Theorem. The Central Limit Theorem shows how every single distribution, discrete or continuous, is related to the normal distribution. This will be the springboard on which we will start our investigation into statistics. It is the theoretical piece that's needed for us to be able to infer something from a population given just a small sample of that population. One example that we'll be exploring is if you poll a small subset of Americans, or any group for that matter, and you'd like to infer what the true population thinks about an issue, you can do that with the central limit theorem behind the scenes. So we'll get to that. So what is the central limit theorem? Well, before I actually state it, let's do a little bit of a recap. We know that if x1, x2, up through x of n are independent and identically distributed random variables, we know from last time that the expected value of x bar is mu. Again, mu, or you could denote this as mu sub x. So when I don't put a subscript x there, I'm thinking of the individual x's there. We also learned that the variance of x bar is sigma squared over n. So this is a result that we proved. And again, this sigma squared is actually the variance of a particular x sub I. But since they are identically distributed, we could just denote that as sigma squared. Okay, so what about so we know this guy's mean, we know this guy's variance. What about the overall distribution of x bar? So we don't have enough theoretical tools to prove what the overall distribution is. So instead, I'd like us to just think about it, and we'll also have the opportunity to see this using computer simulations. So again, x bar takes each of the x sub i's, adds them up, and divides by n. We're taking individual values, or values from each of the individual distributions, adding them up, dividing by n, where each of these guys are random. Well, if you think about it, since this guy is an average, and in fact we know it's centered at mu, then most of the values of x bar's distribution should be clumped around the mean. And in fact, as we get further and further away from the mean, we should have fewer and fewer x bars. Let's think about this in terms of a weight example. So so the underlying weights of Western students have some sort of distribution at the individual level. And we want to, again, sample n students at a time, compute the sample mean, compute this mean, and then what we want to do is we want to create a graph of the results. So let's say the true mean Western weight is, I have no idea, 154 pounds. Well, if you are collecting samples of 100 students at a time, you would expect most of the averages to be around 154. And you'd expect fewer and fewer to be lower and lower than 154 as you get further away, and fewer to be higher and higher than 154. Pause the video and ask yourself, what picture are you seeing? Right, well, hopefully you said, oh, I know what that is. That is just the normal distribution. So x bar is distributed normally. Again, that is not a proof. We don't have the tools to actually prove this piece of the puzzle, but you'll see that in a computer simulation, and hopefully that makes sense from an intuitive standpoint. Okay, so x bar is normal, and I'm going to put that in quotes because if you think about it, if n is 1, then x bar is just one of the x sub i's. And that definitely does not have to be normal at all. If the original xi's happen to be Poisson or uniform, then x bar is definitely not normal. But as n gets larger and larger, this averaging effect occurs, and x bar becomes more and more normal. So as n approaches infinity, x bar approaches a normal distribution. And in fact, we know the mean of that distribution. This we did prove. The mean is going to be mu sub x, or just mu, and the variance is going to be sigma squared over n. Okay, so again, I need to emphasize we did not prove this, and we will not prove this. But we did prove this, and we did prove this. Okay, so I'm going to introduce a new random variable. I'm going to call it W. Seems a little strange. X bar minus mu over sigma over root n. And I want you to pause the video and find the expected value of W and the variance of W. And once we have these pieces along with this, we'll be able to prove the central limit theorem. Okay, so pause the video. Well, let's see. Hopefully you said that the expected value of W is the expected value of x bar minus mu over sigma over root n. Sigma over root n are constant, so we can pull those guys out. So we have the expected value of x bar minus mu. The expected value of a difference is the difference of the expected value, so we have 1 over sigma over root n times the expected value of x bar minus the expected value of mu, but that's just mu because mu is a constant, and mu minus mu is 0, so we get 0 out of this. So the expected value of this random variable is 0. Well, what about the variance of W? What about the variance of W? Well, let's see. The variance of W, that's just going to be the expected value of W squared. Why is that? Because the variance is the expected value of W squared minus the expected value of W squared. Learned that a long time ago. But the expected value of W is just 0. So the variance simplifies to the expected value of W squared. So let's compute that. So this is the expected value of x bar minus mu over sigma over root n quantity squared, because that's what our W is. So we get the expected value of x bar minus mu squared over sigma squared over n. So just algebra, I just square this out. The square of a quotient is the quotient of the squares. Let me flip this guy and bring him out because he's just a constant. But this guy, by definition, is the variance of x bar, just by definition. But the variance of x bar is sigma squared over n. Beautiful. I just get 1 out of this. That's kind of cool. Okay, so why am I introducing this thing? Well, we are now ready to state the central limit theorem. We have all of the pieces that we'll need. And I'll write all the pieces down, and we'll see if you can come up with the punchline. So this is the central limit theorem. So let's let x1, and it also goes by the CLT. Let's let x1, x2, up through x of n be IID. Again, independent and identically distributed with common mean mu and variance sigma squared. Then, as n approaches infinity, x bar minus mu over sigma over root n approaches what? It approaches some distribution, a very specific distribution. So pause the video, see what I wrote here, 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 and here, and see if you can write the punchline. Well, hopefully you said, and admittedly, this is pretty conceptual, so if you didn't get this, don't feel bad. But x bar is becoming more and more normal. We are taking a normal distribution, we're subtracting its mean, and we're dividing by its standard deviation. Sigma over root n is just the standard deviation of x bar, since the variance of x bar is sigma squared over n. Right? The square root of this is sigma over root n. But that means that this is going to approach a standard normal distribution, because we're subtracting its mean and dividing by its standard deviation. And in fact, I gave you the hint right over here. So this guy approaches a normal 0, 1. So we need to think about this. This is crazy, because I'm not saying if the xi's are continuous. I'm not saying if they are discrete. I'm just saying that, hey, as n gets larger and larger, if you take sums of values from here and divide by the number in the sample, divide by n, subtract the parent mean, divide by the standard deviation, that quantity will approach a standard normal distribution. To me, that is unbelievable. But it's true. Okay, so again, this idea is going to be the theoretical groundwork that we need to do statistics. Well, the world of statistics is much more practical, I would say, than the world of theoretical probability. Okay, these are scientists using, or social scientists, physical scientists, using data, using some small subset of data, and what they're trying to do is infer something about a larger group. That's really the gist of statistics. And they need this. We'll see how in the next lecture. But there's a problem, because I'm a scientist, and this whole n approaching infinity business, it's not going to cut it, because I need an actual n to do my computations on. So, historically, and when I say historically, when I went to school, or I feel like it's even talked a lot about now, typically, instead of n being bigger than infinity, n being bigger than 30 is considered, quote unquote, to be infinity. Now, with that said, that might not be a good assumption. So again, this result is used in formulas that scientists then use in the world of statistics. They're counting on this being normal. And this is true that as n gets larger and larger, this does approach a standard normal. And typically n equals 30 is the cutoff that people use when they say, oh yeah, my sample size is large enough. I think this is pretty close to this. But I want to point out that that's not necessarily true. Because if your original distribution is super crazy, super non-normal, then it's just going to take a larger n to make that happen. With that said, there are tests for normality that we're not going to talk about here. But let me also say, for this class, we're just going to kind of hand wave this piece, but I just want you guys to be aware of this when you go on and maybe study this in a statistics class. Okay, so let's do one example with this so we can see how this is used in practice. To be honest, this is kind of a silly example. It's just to show us how to apply this. The real meat and potatoes is going to come next lecture, where we see the power of this statement. So just an example to see if we can apply this theorem. Let's let x bar be the mean of a random sample of size 50 with mu equal to 60, sigma squared equal to 10. I want to know the probability that x bar is bigger than 70. Okay, so actually a couple of things. So first off, we are going to compute this mean, this probability of this occurring. And if you look at the question, something is missing, and we can still solve the problem. So what is missing? We don't even know what the parent distribution is. So this is kind of shocking that we can actually do this. However, that's the power of this statement. Doesn't matter what the original distribution is, we could still ask questions about x bar. You know, and actually before I said, hey, this is kind of a silly example, it's just to have us understand this, but actually it's not a silly example if I explain the context. So let me do that. Let me explain why we even care about something like this. So let's think about this. Let's say you're a scientist and you're studying some phenomena. And it's accepted that for the thing that you're measuring, let's say this is temperature. Let's say all scientists think, or most scientists think, that the true mean temperature is 60. Okay, they think the true mean is 60. It's been published in papers, lots and lots of papers. Well, you don't think it's true. Let's say you think this whole global warming thing is happening, and you think it's higher than 60. So you go out and you start collecting data, and you actually get a sample mean. So a sample mean, that means, or signifies from some small subset, you get the probability, you get that your sample mean is 70 degrees. So everybody thinks the true mean is 60. You think it's higher by your data, and you go out there, you get 70. Well, 70 is higher than 60, that's a fact. But the problem is, depending on how spread out the distribution, the 70 might not be a statistically significant number. In other words, let's say this distribution is super spread out. Somebody says it's 60, you get 70. Well, big deal. Maybe that just has to do with the random variation of the sample that you took. But you can actually compute this value using the Central Limit Theorem. And if you get a value that is really low, so let's say you get a value of 0.0003. So let's see what we would have to conclude. Somebody tells you it's 60 with variance of 10. You compute this probability of something that you actually got. So so you actually got 70, and then you ask, hey, what's the probability that x bar is actually greater or equal to 70? Again, that the equal doesn't matter since it's continuous. So what's the probability that x bar is greater or equal to 70 given this 60? You'll be able to compute that probability using the Central Limit Theorem. If you get 0.001 or 0.003, well then I don't believe this statement. Because somebody's telling me this is true, I get this number, I compute its probability, the probability of that happening is very low, so I no longer believe this. You have just performed your first hypothesis test. More on that in a couple of lectures. But back to this. Let's actually compute this number. I just threw some numbers out there. So how do we compute this? Well, we use the Central Limit Theorem. This is telling me that I could take x bar minus mu over sigma over root n. Well, if I do that on this side, I have to do it on this side. minus mu over sigma over root n and this is a number that we can just work out. Okay, we can work that out using the normal CDF. Boom. So we're computing a probability on a sample mean without knowing anything about the underlying distribution due to the central limit theorem. That's the power of the central limit theorem. All right, that's all I have to say about that. I think this might be a good lecture to watch a couple of times or check out the highlights. Make sure that you're on board with the central limit theorem because this will be popping up several times in the next several lectures when we start looking at statistics. Thanks for listening. I hope you enjoyed the lecture, and I will see you guys next time.